Hello, and welcome to the video accompaniment for Chapter 5, Section 4. In this section, we're talking about bijective functions. Notice that there's also an activity sheet that goes along with this section. This activity sheet is meant to guide you through how to prove that a function is injective, surjective, or bijective, and it'll have you make some arguments about how the cardinalities of sets relate to the existence of functions of certain types, whether injective, surjective, or bijective. So you could do that before this, or you could do that after this. That's sort of up to you. You could do it along with the video if you want. There's no certain order I think would be best for this one. So in this video, and by the end of this video, you'll be able to recognize when a function is injective, surjective, or bijective just from looking at a diagram or the graph. So not proving if it has these properties, but just being able to tell from a graph right away what properties it's going to have. And we'll talk a little bit about how the existence of a bijective function, what that has to deal with the cardinality of the underlying sets. And that's going to turn out to be really important for the next video, the next section of this chapter. All right, let's get started. So we'll start by just taking a look at an example, and actually we'll go through a few examples, and each one I'm going to draw a diagram, blobs and arrows, and we'll see in the diagram how we can tell if the function is injective, surjective, or bijective, or none of the above. So here we have this function defined from A to B. I'll go ahead and draw my blobs. Hopefully you're starting to see what a benefit it is to being able to depict something visually. Normally in math, we can't depict everything visually, but if we sort of start with something small, something discrete, depict that visually, that gives us an idea of how to do it when we can't visualize it. So, maybe we start with two-dimensional drawings, and maybe we draw some three-dimensional drawings, and that maybe will let us generalize to n dimensions for n greater than or equal to 4. So the same thing here. These diagrams help when we have discrete sets and finite discrete sets. But the ideas are going to generalize to not discrete sets and infinite sets as well. And moreover, they just help us understand better what these things mean. All right, let's go ahead and draw our function. 1 goes to x, 2 goes to z, 3 goes to w, 4 goes to x, and 5 goes to y. So remember the definitions for injective, surjective, and bijective. Injective, in terms of diagrams, injective means that no element in the codomain is hit twice. So that is, every element of the codomain has no more than one arrow going to it. There might be some with no arrows going to them, and it can still be injective, so long as everything has no more than one arrow going to it. That's injective. Remember, surjective means everything in the codomain is hit by something in the domain. So that is, everything in the codomain has at least one arrow going to it. So maybe that can be helpful for injective. Surjective, it's talking about things in the codomain and the existence of these arrows to them or not, So in this case, I'll draw your attention to the element x, which was hit by 2 elements. 1 and 4 both went to x. So that, because of this existence of this element x that's hit by 2 distinct elements, this tells us that f is not injective. And then looking at the entire codomain, you can see that every element has at least one arrow going to it. And so we could say that f is surjective. Remember these other words that go along with injective. So this means 1 to 1, and surjective also use the term onto. Onto, sur means on, or on top of. And so you can think these sometimes help me. Onto, surjective means the set A is sort of on top of the set B, that everything is hit by something in A. Okay, let's look at another example. All right, so a similar example. I'll draw my blobs again. A little bit different sets and a different function between them. So here we just have 3 elements in A, and here we have 4 elements in B. 1, 2, 3. W, X, Y, Z. And let's draw our function. 1 goes to X, 2 goes to Z, and 3 goes to W. So notice that Y is not hit by anything. So we can conclude F is not surjective, it's not onto. But then notice that every element of the codomain, I haven't been labeling these, this is A and this is B, hopefully you assumed that. Everything in the codomain has at most 1 arrow going to it, right? Y has 0, that's okay, as long as there's not 2 arrows going to the same element of B. That we can conclude that F is injective. It is 1-to-1. And since it's not surjective, it's not bijective. I forgot to mention that in the last example. That last one, we had a surjective function that was not injective. Remember, bijective just means it's both injective and surjective. And so we could say for this one, F is not bijective, but it is injective. Let's look at another one. All right, so similar setup as the last one. We have the same sets as the last example, but a different function between them. So I'll go ahead and draw the sets again. 1, 2, 3. And then W, X, Y, and Z. W, X, Y, Z. And let's see here. Again, this is the set A. This is the set B. I'll use green again. So 1 goes to X. 2 goes to X. And 3 goes to W. So which properties does this function possess? Is it injective? For that we check again. We check the codomain. Well, X has 2 elements that go to it, 1 and 2, and so that means it's not injective. And then notice that, well, there exists an element of B such that nothing is assigned to it, and so it's not surjective. And so for sure, right, to be bijective, it has to be both injective and surjective. It's not either here, so definitely F is not bijective. All right, let's keep moving along. So another similar setup. If you're kind of trying to predict why I'm coming up with these examples, we've seen an example of a function f which is injective but not surjective. We've seen one that's surjective but not injective. We've seen one that's neither. So maybe we'll have one here that does both. All right, let's graph our function. 1 goes to Z. 2 goes to W. 3 goes to Y. and 4 goes to x. So, okay, what properties does it possess? Well, is it injective? Do you see any two arrows going to the same element of the codomain? No, so it's injective. Is it surjective? Yep, everything in the codomain is hit by something in the domain. Hence, together those imply F is bijective. So that's pretty cool. Notice what's happening here is that everything in the domain is matched up with exactly one thing in the codomain. What we have here is a matching between the elements of A and the elements of B, right? We call this a one-to-one correspondence between those elements. And this is really neat because when we have this, it should be easy to sort of think through this that, well, we have to have the same number of elements in both sets. That really the existence of this bijective function is only happening because the two sets have the same cardinality. We'll talk about that a little bit later. First, I want to move away from these blobs and arrows and talk about how to detect these properties in a graph. So maybe a function from the real numbers to the real numbers, something like that we can't depict with blobs and arrows. So let's take a look at something like that. So like I said, we'll take a look at a function from the real numbers to the real numbers. Here it's this polynomial. F of x is x squared minus 4x plus 4. And we want to determine what properties of injective, surjective, bijective apply to F, if any. So maybe you remember back to a pre-calculus or calculus class or an algebra class where you want to graph quadratic functions. One good thing to do is to try to get it into vertex form. And this one way you can do that is to factor it. So notice that this thing is the same as x minus 2 squared. That it's really equal to that. And so that'll help us graph it. So instead of doing blobs and arrows, because that would make me have to draw an infinite number of elements, it wouldn't look good. But a graph works well for situations like this. So maybe let me go 1, 2, 3, 4, -1, -2, -3. Let me go. What should I do for this one? Let me think. Let's go 1, 2, 3, 4, 5, 6, 7, 8. Sure, let's do that. And then negatives, -1, -2, -3, -4, -5, -6, -7, 1, -1, 1, so that my scale is clear. All right, let's graph this. When I have it in vertex form like this, looks like a regular parabola. This looks like x squared, but shifted right by 2 units. So here's 2 right there. That'll be the vertex. Since it doesn't have a negative sitting outside of it, it's going to be pointing up. It'll be concave up. When I plug 1 in, -1, I'll square that. I get 1. When I plug 3 in, I'll square that. I'll get 1. Oh my gosh, PowerPoint. Sometimes it's really bad when I have my thing in the same place for too long. And when I plug 4 in, I should get 1, 2, 3, 4. When I plug 0 in, I should also get 4. 1, 2, 3, 4. So right now I'm almost graphing it as if it was from the natural numbers to the natural numbers, but then I know since this is real to real, that I should draw lines that follow this. Remember that in any case, a graph is a collection of ordered pairs. When we have an infinite number of those ordered pairs really packed tightly together, in the case of this continuous function, there's so many ordered pairs that it looks like a line. Hence, we draw a line for it. But if we were going from natural numbers to natural numbers, a graph would just look like a collection of points in the plane. So is this injective, surjective, or bijective? So we want to test elements of the codomain. Certainly, right, this is a function. We know this is a function because it passes the vertical line test. A lot of people like to use that test. If I draw a vertical line anywhere, it'll only hit the graph. It'll hit the graph at exactly 1 point. That's the vertical line test. That tells us it's a function. There'll be a similar geometric test for injective. So remember, with injectivity, we want to test elements of the codomain, and we want to know, are there, for every element of the codomain, is there, I guess, how many elements of the domain are assigned to that? And so what we could do for anything in the codomain, so along the y-axis here, right, this is like my y-axis, this is my x-axis. So what I can do is I can draw a line, a horizontal line this time, to represent a value y, so something in the codomain. Notice that it hits our graph at 2 points. Hence, there are 2 values that are associated with this value. This is the value y equals 4. If you couldn't tell by my drawing, I drew it at 4, or tried to at least. And so this means there's 2 things that are associated with 4, 2 things in the domain that are mapped to 4. Hence, it's not injective. Not injective. So just like for the vertical line test, we can detect if a graph like this is a function. If we want to detect if it's injective, we can try these horizontal lines. Now, something similar, we'll also draw horizontal lines to test if it's surjective. What we're looking for here for surjective is that the graph just touches any horizontal line at least once. So this line that I drew here, we can't conclude anything about the surjectivity just from that single line. It's okay if it crosses it twice. But the problem arises with values down here. So say at y equals -6. At y equals -6, there are no values of x that spit out -6, right? X minus 2 squared, that's the square of a real number. And so this is always greater than or equal to 0. So there are, this function doesn't spit out any negative numbers. We can see that with the horizontal line test down here. There are no input values that are associated with the output value of -6. And so this tells us that it's not surjective. So this function here, it's not surjective and not injective. What we would be looking for is that every horizontal line intersects our graph at exactly 1 point. That would mean it's both injective and surjective, and hence bijective. Now, an example of something that does this would be a line that's not vertical and not horizontal. Any line, so any linear function, will be both injective and surjective, and hence bijective, because every horizontal line will intersect that line at exactly 1 point. So that's the deal. That's how we can see from these more traditional graphs how to detect these properties. All right, let's move on. Last thing I want to talk about, and the activity gets at this, is the relationship between existence of bijective functions and the cardinality of their underlying sets. So in the activity, you'll make some arguments that support each of these claims. So if there exists an injective function, f from a to b, actually in the activity this will be stated, the negation of this, right? If there doesn't exist, or if the cardinality of A is greater than the cardinality of B, it's impossible to find an injective function. And therefore, if there does exist an injective function, we can conclude that the cardinality of A is less than or equal to the cardinality of B. And if there exists a surjective function from A to B, then that's true if and only if the cardinality of A is greater than or equal to the cardinality of B. So the magic happens when we have a bijective function. That is, if both of these things are true, well, look, I have the inequality in both directions. And so I'd be able to conclude from both of these, if I have a bijective function, that the cardinality of A is equal to the cardinality of B. Now, this is true for finite sets. And so while with finite sets, we could just count the cardinality of each of the sets to determine if they're the same cardinality or not, this gives us an alternative way. We could show that there exists a bijective function and conclude that the cardinality has to be the same. But that's not the real power in this observation. The real power here is our ability to now extend the definition of same cardinality to infinite sets. So before all this, all we could say about infinite sets is that, well, they were infinite. They had infinite cardinality. We couldn't talk anything about infinite sets having the same cardinality or not because we didn't have a definition for that. What this observation gives us is that definition. We extend this observation that we have for all finite sets and extend it to infinite sets. So that is, we can define this this idea of same cardinality. Two sets A and B, finite or infinite, are said to have the same cardinality if there exists a bijective function from A to B, or from B to A. So that's what the same cardinality really means. We'll take this and run with it and start looking at infinite sets in the next section. And that's where we're going to see some really fun stuff, right? Before this class, you might have thought, well, anything that's infinite is infinite, right? Infinity plus 1 is the same as infinity. You can't get bigger than infinity. Well, let's see if that really holds true.